Good day. Today we are going to discuss the first topic for the probability theory. Let's have the introduction to the basic concept. So, so let's have the introduction to the basic concept of the probability theory. Okay, so the origin of the probability theory lies in the physical observation associated with the games of chance. It was found out that if an unbiased coin is tossed independently n times, uh, there um, where n is very large, the relative frequency of heads, that is the ratio of the number of heads to the total number of tosses, is very likely to be very close to one half. Similarly, if a card is drawn from a perfectly shuffled deck and then is replaced, the deck is reshuffled and the process is repeated over and over again, there is convergence of the relative frequency of spade to one fourth. In the card experiment, there are 52 possible outcomes when a single card is drawn. There is no reason to favor one outcome over the other. That is called the principle of insufficient reason or of least astonishment. And uh, the early workers in probability took as the probability of obtaining a spade the number of the favorable outcomes divided by the total number of outcome. That is 13 over 52 or one fourth. This kind of concept is called classical definition of probability. The probability of an event is the number of outcomes favorable to the event divided by the total number of outcomes, where all outcomes are equally likely. Is the first of all restrictive. It considers only experiment with finite number of outcomes. And more seriously, circular, no matter how you look at it, equally likely essentially means equally probable. And thus, we are using the concept of the probability to define the probability itself. Um, we cannot use this idea as the basis for the mathematical theory of probability. However, the early probabilities were not preventive from deriving any valid and useful results. Similarly, an attempt at a frequency distribution of probability will cause trouble if the, let's say, let's say that if uh, S sub n uh, is the number of occurrences of an event in n independent performances of experiment, we expect physically that the relative frequency, okay, so we expect that the relative frequency of S sub n over n, okay, should converge to a limit. However, we cannot assert that the limit exists in a mathematical sense. In the case of tossing of unbiased coin, we expect, okay, so let's say that uh, this is the um, unbiased coin. We expect that uh, the the S sub n over n will converge to one half. But a conceivable outcome of the process is that the coin will keep coming up heads forever. In other words, it is possible, okay, it is possible that the S sub n over n will converge to 1, or S sub n over n will converge to any number between 0 and 1, or that S sub n over n has no limit at all. So in this discussion, we will introduce the concept that um, to be the concepts that are to be used in the construction of mathematical theory of probability. The first ingredient that we need to set in mind is the concept of sample space. So we have that omega as our symbol. Okay, sample space representing the collection of possible outcomes of a random experiment. For example, let's say head and tail. Okay, let's say T for the tail and then H for the head of the unbiased coin. Okay, so if the coin is tossed once, we have the sample space of course, head and tail. Okay, if the coin is tossed twice, if that would be the case, then we have the sample space of course, we have head, then head tail, then tail head, and then tail tail. Okay. In this case, one performance of the experiment correspond to two tosses of coin. Okay. If a single die is tossed, okay, we may take the sample space consists of 6 points. We say 1, 2, 3, 4, 5, 6. Okay. However, another possible sample space consists of 2 points corresponding to outcomes of, let's say, n is even and n is odd, where n is the result of the toast. Thus, different sample spaces can be associated with the same experiment. The nature of the particular problem under consideration will dictate which sample space is to be used. If we are interested, for example, in whether or not the n is greater than or equal to 3 in the given performance of the experiment, the second sample space corresponding to n even and n odd will not be useful to us. In general, the only physical requirement on the sample space is that a given performance of the experiment must produce a result corresponding to exactly one of the points of the sample space. We have yet to know mathematical requirements on sample space. It is simply a set of points. Um, Next concept that we have to set in mind is the notion of the event. When we say event, an event associated with the random experiment corresponds to a question about the experiment that has a yes or a no answer. And this, in turn, is associated with a subset of the sample space. Okay, for example, if the coin is tossed once, then we have a sample space of HH, HT, TH, and TT. The number of heads is less than or equal to 1 will be the condition that either occurs or does not occur in a given performance of experiment. That is, after the experiment is performed, the question, let's write the question. The question is the number of heads less than or equal to 1 can be answered with a yes or a no. Okay, we take note that the subset of the sample space corresponding to yes. Okay, let's take note that uh, our sample space would be head head. We have head tail, tail head, and tail tail. Okay. Uh, Again, the subset of the sample space corresponding to a yes, okay, is, let's say A is yes, okay, would be all those points with the head with uh, we have tail. So we have head, tail, tail, head, and tail, tail. Okay. If the outcome of the experiment is head tail, tail head, or tail tail, the answer of the question is the number of heads is less than or equal to 1 will be yes. If the outcome is head head, the answer will be no. Similarly, the subset of the sample head associated with the event that the result of the first toast is the same as the result of the second toast, okay, then we could have, let's say, let's call it B. Then the sample space of the B where the first result is equal to the second result would be, you have the head head and tail tail. In other words, um, we could say that an event is defined as the subset of the sample space that is a collection of points of the sample space. Okay. Um, Now, we have to bear in mind that the events will be denoted by capital letters at the beginning of the English alphabet, such as A, B, C, and so on. So an event may be characterized by listing of all of its points or equivalently by describing a condition under which the event will occur. Okay, for example, if we have a coin tossing experiment, okay, just considered we are going to write, okay, we could write that one as uh, this one, uh, the number of heads is less than or equal to 1. Okay, this expression, okay, we could have this one as the subset A uh, is the set consisting of those outcomes which satisfy the condition that the number of the heads is less than or equal to 1. Or simply, A is the event that the number of heads is less than or equal to 1. The event A consists of the points that we have discussed in the previous slide. We have the HT, TT, the HT, the TH, and TT. Therefore, we could write that one the way that we have written that in the previous slide. Okay, which can also be read as A is the event consisting of the points TH, HT, and TT. Okay, in another example that we had in our previous slide, okay, if B is the event that the result of the first toast is the same as the second result of the second toast, we may describe B by writing, we could have B would be first toast is equal to second toast. Okay. Or, of course, equivalently, we could have the B is equal to HH or HHTT. Okay. So, I'm sorry. Each point belonging to event A is said to be favorable to A. The event A will occur in the given performance of the experiment if and only if the outcome of the experiment correspond to the points of A. The entire sample space omega is said to be sure or certain event if must occur on any given performance of the experiment. On the other hand, the event consisting of none of the points of the sample space, that is empty set, is called impossible event. Um, it can be never occur in the given performance of the experiment. Okay, that's the basic concept of the probability theory. So let's move to algebra of events, the Boolean uh, algebra. Before taking about the experiment of probabilities to events, we introduce some operations by which new events are formed from old ones. So these operations corresponds to the construction of the compound sentences by use of the connectives or the and not. Okay, let the events A and B be events in the same sample space. Define the union of A and B denoted by A union B as the set consisting of those points belonging to either A or B or both. Unless otherwise specified, the word or will have for us the inclusive connotation. In other words, the statement P or Q will always means P or Q or both. Define the intersection of A and B written as A intersect B as the set of points that belongs to both A and B. Okay, we have also defined the uh, complement of A written as A raised to C as the set of points which do not belongs to A. Now, let's have to consider, for example, uh, sige, uh, the experiment involving the toss of a single die where with N, okay, let's take note that, okay, N is the result. Take sample space where 6 points correspond to N. So let's say we have the N is 1, 2, 3, 4, 5, 6. Okay, so if our A is even and our B would be N greater than or equal to 3. In this case, we could write that the A union to B would be N is even, or okay, we could have this one as N is even or N is greater than or equal to 3. So if we are going to have the list of those elements, then we could have 2, 3, 4, 5, 6. Then if we are going to have the A intersect to B, then we could have the N is even and N is greater than or equal to 3. If we have to have the least, then it could be 4, 6. Then if we are going to have the complement of A, then N is not even. If we are going to have the least, then we have 1, 3, 5. Okay. Now, if we are going to have uh, the schematic representation, which is called the Venn diagram, of course, we could have this kind of illustration. So if we are going to illustrate the A union B in the uh, Venn diagram or the schematic representation, then if this is, let's say this is our A and this is our B in our Venn diagram, of course, this would be the A union B. Okay. Now, if we are going to have the A intersect B, and this is our A, this is our B, in our Venn diagram, this would be our intersection. And of course, if we are going to illustrate in the schematic representation the complement of A, then if this is our A in a given space, then this is our complement. Okay, very common. So the next that we are going to consider is we have to define the union of n events, a sub 1, a sub 2 to a sub n. We have this one as in our notion. We have the a sub 1 union to all the events to a sub n, or simply we have this kind of notion. This one. Okay, so the union of all events from 1 uh, to a sub n. Okay, as the set consists of those points which belongs to at least one of the events a sub 1, a sub 2 up to a sub n. Similarly, define the union of an infinite sequence of events a sub 1 to a sub 2 to so on as the set of the points belonging to at least one of the events a sub 1, a sub 2 up to infinity. So we have that notion as a sub 1 union to a sub 2 to union to infinity, or we have this kind of notion. So the union of all of the events of A. Okay. So next that we are going to consider is define the intersection of n events a sub 1 to a sub n as the set of points belonging to all the events of a sub 1 up to a sub n. So we have that notion that a sub 1 intersect to a sub 2 up to a sub n. Or simply, we have this notion, the intersection of all events of events A. Similarly, define the intersection of an infinite sequence of events as a set of the points belonging to all events of the sequence with that notion. Okay. Now, if if we go back to our example that our A is even and uh, B is n greater than or equal to 3, okay, and then say let's write A is even, and set of n which are even, then our B is n greater than or equal to 3. Let's say our C would be n equals 1 or n equals 5. Now, if we are going to have um, A union to B union to C, okay, if we are going to if we are going to have the union of A, B, and C, this is the sample space. Okay, now if we are going to have A union to the complement of B union to C, okay, this is simply uh, 1, 2, okay. So this is simply 1, 2, 4, 5, 6. Why? Our A is 2, 4, 6. The complement of B is 1, 2. And our C is 1, 5. Now, if we are going to get the union of all the events, then we have 1, 2, 4, 5, and 6. Now, if we are going to have the union of A and C intersect to the, let's say, A union to B, the complement of this, okay. So the answer would be uh, 1, 2, 5. Okay. Why? Remember that A union to C would be 1, 2, 4, 5, 6. And of course, the complement of the intersection of A and B would be 4 and 6. So if we are going to get the intersection of those elements, then we have 1, 2, and 5. So two events in a sample space are said to be mutually exclusive or disjoint if A and B have no points in common. That is, it is impossible that both A and B occurs during the same performance of experiment. In symbols, we have A and B are mutually exclusive if A intersect to B is null. In general, the events A sub 1, A sub 2 up to A sub n are said to be mutually exclusive if no two of the events have common point or point in common. That is, no more than one of the events can occur during the same performance of experiment. So if we are going to write that one in symbolic notion, okay, this condition can be write as we have A sub I intersect to A sub j, okay, is null, okay, for I not equal to j. Okay. Similarly, infinitely many events A sub 1, A sub 2, up to so on are said to be mutually exclusive if, of course, we don't have intersection of the events. Okay, so we have A sub I intersect to A sub j, which is a null for I not equal to j. In some ways, the algebra of event is similar to the algebra of real numbers, with union corresponding to addition and intersection to multiplication. Okay. For example, okay, let's have an example. um, the common notion, okay, we have the A union to B is of course equal to B union to A, or we could have A intersect to B is equal to B intersect to A. And then we also have, we learned this one in our college, this one, A union to uh, B union to C, which can be written also as A union to B union to C. And then we also have A intersect to the union of B and intersection rather of C, which is equal to the intersection of B and A and B intersect to C. Okay. Furthermore, uh, we could prove that the events A, B, and C are the same sample space. Then we could have this one, um, A intersect to the union of B and C, which is the same as the intersection of A and B, okay, union to the intersection of A and C. Okay, there are several ways to establish this. For example, we can verify that the sets of both the left and right of the equality are represented by the same area in the Venn diagram. Okay, another approach. Okay, another approach that we could use is the definitions of the intersection in intersection to show that the set in question have precisely the same members. That is, we show that any point which belongs to the set on the left necessarily belongs to the set on the right, and conversely. Okay, so let's have an example. We say that an X is an element of A union to B, A intersect to the union of B and C, which implies that X is an element of A. And we could say also that X is an element of uh, B union to C. This also implies that, of course, as X element of A, okay, it also mean that the X is an element of B, or X is an element of C. Now, case 1, X is element of B. Then X is element of A and X is element of B. So X is an element of A intersect to B. So we could say that X is an element of the uh, intersection of A and B union to the intersection of A and C. So that's our case 1. Case 2, X is element of C. Then X is element of A, and X is element of C. So X is element of A intersect to C. So we could also say that X is uh, element of the intersection between A and B union to the intersection of A and C. So since we have these two cases, thus we could now say that the X is an element of A intersect to the union of B and C, which implies that X is an element of the intersection of A and B union to the intersection of A and C. That is okay. That is A intersect to B union of B and C, which is a subset, okay, of uh, A intersect to B union to A intersect C. So in this case, we could have to bear in mind that the subset is a subset of itself. Okay. Conversely, okay, let's have the converse na. Conversely, okay, let X is an element of intersection of A and B union to the intersection of A, C. Then X is an element of A intersect to B, or X is an element of A intersect to C. So in this case, we have two cases. Case 1, okay, for case 1, we have X element of A intersect to B. Then X is an element of B. So X is an element of the union of B and C. So the X is an element of A. Let's write this one below. So let's rewrite. X is an element of A intersect to the union of B and C. Our case 2, we have X is element of A intersect to C. Then X is element of C. So X is element of the union of B and C. So we could have X is an element of A intersect to the union of B and C. So we could conclude that uh, the intersection of A and B union to the intersection of A and C is a subset of A union to the intersection of B and C. Therefore, the A intersect to the union of B and C is equal to the uh, union of the intersection of A and B and A and C. Okay. Another example, okay, would be, let's say, you have the union of all the events A, so say, the complement of the union of all events A. So you have A sub 1, union to A sub 2, union so on to the union of A sub n, then complement would be equal to the intersection of its complement. So this one. So to prove that we have this one, okay, you have X is an element of A sub 1 union to so on up to A sub n, then gets its complement, okay, which implies double implication rather that X is not the element of A sub 1 union to all its uh, events of A, which also, okay, double implication, uh, it is not the case that X belongs to at least one of the A sub I, which also, okay, double implies that X is an element to none of the A sub I, which also implies that X is an element of the complement of A sub I for all I, which also implies that X is an element of the intersection, not I, 1, that should be 1. The intersection, not intersect, the intersection of the complement of A sub I, okay, up to the intersection of the complement of A sub n. So an identical argument shows that we could now say that the union of uh, the actually this is the complement. The complement of the union of all A sub I is equal to the intersection of uh, the complement of A sub I Okay. So there are uh, many uh, identities. Actually, these are called identities. There are many identities that we have in our college days, especially the De Morgan's law. Okay, so those are the concepts that we have learned in our um, college days. So let's have the last example. So for our last example, let's say that the sample space uh, is the set of non-negative real numbers. So non-negative real numbers. Okay, so our a sub n would be you have 0, 1 minus 1 over n, which is can be written as the set of x elements to the sample space such that x is greater than equal to 0 but less than or equal to 1 minus 1 over n. Okay, where our n, 1, 2, so on. Okay, so this can be a read. Okay, actually this can be read as a sub n is a set consisting of those points x in the sample space such that x is greater than or equal to 0 but less than or equal to 1 minus 1 over n. Okay, in simplest term, we could also write that one as a sub n is equal to set of x, okay, such that x is greater than equal to 0 but less than or equal to 1 minus 1 over n. So in this case, if we are going to look for the intersection of all the events A, so the intersection of all the events, okay, n is equal to 1 to infinity, this is actually just 0, 1, half open. Or it can be written as uh, a set of x such that x is less greater than equal to 0 but greater than 1. Okay, now if we're going to have the intersection of all events, okay, we could have so, dito na lang. The intersection of all the events A, 1 to infinity, is actually the 0. Okay. Now, if we have this one, the complement of the intersection of all events A. Okay, so, and not intersect, the union pala. The union of all events A from 1 to infinity and gets its complement, then we could have the complement of these numbers, which would be from 1 to infinity, which implies, not implies, which is can be written as the set of x such that x is greater than equal to 1. Okay, using the concept of De Morgan's law. Okay, so that's the discussion that we have for today. Thank you for listening.